Welcome. So let's talk about chapter 5. So in chapter 5, we are going to start off by talking about sequences. Now, some of you may have seen sequences in the past, especially for those of you who have done Calculus 2. Hopefully, you've also seen in other areas. Sequences are really kind of a list of numbers, and we're trying to look for the pattern. Another way to think about it more accurately is they're actually a function, and we'll talk about the actual definition. Let me start with a very simple example. Suppose you're counting the number of ancestors you have. Well, you have 2 parents, 4 grandparents, 8 great grandparents, and so forth. And we can keep doing this count and so forth. Well, the position, we could call this first spot where the 2 is position 1, the 4 position 2, 8 position 3, and so forth and so on. This positioning or indexing can start. By the way, quick note, we can start an index anywhere we want. For those of you who've used Python, this happens in C and other programming languages, often they start at indexing at 0, but you can even use negative indexes, actually, if you know how to use things correctly. So indexes can start wherever we want, and we can call out specific values of this. But if I started looking this list of numbers or sequence, I can notice that the 2 is 2 to the first power. That's a nice correlation between the 2 and the 1. 4 is 2 to the second power, 2 to 2. Position 3 was 8, which happens to be 2 to the third power, and so forth, so that a sub k, where a sub k is the number of k ancestors k generations back, because my parents are 1 generation back, grandparents 2 generations back, etc., would be 2 to the k. That's how they look. Now we get the idea. Further, let's introduce the formal definition. Again, we talked about this being important in sequences, in proofs. But a sequence is a function whose domain is some subset of integers. It can be all the integers between 2 given integers, or all the integers that are greater than some integer. We often don't do it all the integers or less. So usually we have a starting integer, and then we sometimes have a stopping integer, and sometimes we don't. That's usually how sequences are designed. But it's a function, which means there's an input, which is an integer, and output, which is whatever the value is in the sequence. We call each of these things like a sub n is a term. This is a sub m plus 1. So this is a sequence that starts at m and ends at n. Those are my indexes. And we are going to keep going until we get a final term. But if I have these dots, so back here, I ended at a sub n. But if I put on just a bunch of dots, so notice both of them have dots, and those dots imply that the pattern continues until we reach this point. If we don't put an ending, it implies it goes on forever. So it's infinite sequence. We're not going to spend a lot of time in this class on infinite sequences because that's really more of the area of calculus. We're going to talk more about what is the pattern, what is the formula for a sequence. Even if it goes on forever, we want the formula, whereas in calculus, you asked questions like, does this converge? Yes or no? And how do you know that? And then you can also use that to prove other things, such as, well, technically limits of a function. So we also want what's called an explicit formula or closed formula or general formula. There's lots of different names of it, where I get something like, sorry, wrong direction, this. This is a closed formula because I can literally plug in k and I get what the number is. There are other sequences out there that is not possible for, and that is really annoying and hard and frustrating. But that's our goal, is to come up with something like this. All right, so let's look at 2 examples of this. I have a sub k, which is equal to k over k plus 1. And notice it tells me that's when k is bigger than or equal to 1. So it's starting when k is 1, gets bigger. B sub I, on the other hand, is I minus 1 over I, where I is bigger than or equal to 2. So just so you can start, I'm going to start, and let's talk about a sub 1. What is a sub 1? I'm going to write this down so you can really see. A sub 1 would equal 1 over 1 plus 1, or 1/2. A sub 2, on the other hand, would be 2 over 2 plus 1. So notice I plugged in the 2 where there was the k. And that gives me 2/3. So with this in mind, I want you to pause the video. I want you to find the first 5 terms of both of these sequences. Go. All right, so if you did that, you should have ended up with these sequences of numbers. And the interesting enough is if you go through them, you'll notice that they are actually the same exact terms in both sequences, their first 5 terms. But they started at different indexes and their formulas were different. And this gets at an idea that it's critical to not just have the formula for us, but to know where does it start. That's really, really important. So whenever we're dealing with these things, we need to identify. So let's look at some more. So this is actually a very specific one I want to play around with. This is called an alternating sequence. And it's important. We're going to start at 0. Remember, anything to the 0 power is just 1, except 0. And if I do this, I have -1 to the 0 power, which is 1, -1 to the first power, which is -1, -1 to the second power, which is 1, and so forth and so on, which means it's simply bouncing back and forth between 1 and -1. This is a very, very common sequence. It plays a sub role in a lot of other sequences, and it becomes a kind of a driving force for us because we're going to use it. All right, so I now have a challenge for you. I want you to kind of play with this. I want you to really try this one. On a piece of paper, I want you to pause the video. Can you find a closed formula for this thing? And remember, part of the closed formula is you need something in terms of, let's say, K or N, and you need to find when that starts. Does it start at 0, start at 1, to start at 2, start at -1? You need to do all those things. So go ahead and pause the video and try that. All right, so let's say you did it. If you were stumped, I'm gonna start on the process. And as soon as you see something, I want you to pause the video and jump in and try to go ahead. I'm going to break this down into multiple different parts. So the first thing I'm going to do is I'm literally going to rewrite the sequence, but I'm going to rewrite it in a way that probably will reveal a secret. First, I can rewrite 1 as 1 over 1. I can write that as a fraction. Now all of them are fractions. I can write the second term as -1 over 4. Third term as 1 over 9. The fourth term as -1 over 16. The fifth term as 1 over 25. And I'm just going to go there. I'm not going to keep going, but you can kind of see the idea, the breakdown. Okay, so first off, that maybe you saw something. Now here's a kind of a clue that helps break it down further. What if I break this into a numerator sequence and a denominator sequence? All right, so my numerator sequence would be 1, -1, 1, -1, 1. Oh, wait. Can you find a formula for the numerator sequence? So maybe you have that one. The denominator sequence is going to be 1, 4, 9, 16, 25. Can you figure out a formula for this? So if you've got those, you go ahead and pause the video and try if you didn't already figure it out. But let's come back to this one. Well, this one, we did this before where we did -1 to the K for K bigger than equal to 0. Remember we did that. That was just the alternating sequence we just did. And if you're taking notes, you probably had that one in your toolbox. That's really easy. It's beautiful. It's nice. Okay. Look at the second one. Well, the denominator sequence, you might notice these are all perfect squares. So this could write as K squared. But notice the first term would be 1 squared. So this would be for K bigger than equal to 1. Oh, wait. I can't use these as they are right now because they're actually off. I have one starting at 0 and one starting at 1. So we have to kind of make some decisions here. So what we can do is we can say, okay, so this first sequence, if I have this start at 1, so let me get out my eraser for a second. I'm gonna have to get rid of my K. I got rid of my exponent. It's still -1 to a power. But so let's say I want to make this first one start at 1. Well, what power can -1 be raised to and still give me +1? Well, obviously I can't raise it to the first power because that would be a -1, but I could raise it to the second power. So I could actually take this as K plus 1 as my exponent. And now this all works. Awesome. So notice this actually would be the formula where I could draw the line here. And now I have a fraction using my two things. But what if we wanted to start at k is bigger than or equal to 0? Well, the first one, the numerator can obviously be negative 1 to the k. That works. But how do I do this one? Well, if I start at 0, what if I did 0 plus 1 squared? That would still work. This one would then be 1 plus 1 squared plus, and so forth. So I could actually have this as k plus 1 squared. So using some of our things, we can manipulate them ever so slightly and be like, so I have to define, where does it start? Does it start at 1? Does it start at 0? I could have started this at 5, and that would have just modified the exponents a little bit differently, or the denominator has started a little bit differently, and we can manipulate this over and over again. So as we work through this, it's all about breaking it down again into all the different parts. In addition, we can keep recognizing, oh, I know an oscillating one, but it has to start at some value. So if I start at k, at 0, then we got problems. So you actually end up with two different formulas again that here they are kind of written out nicely. I really like this beautiful write-up of them, where a sub k is equal to negative 1 to the k plus 1 over k squared, or a sub k equals negative 1 to the k over k plus 1 squared. And here's the key thing. You need to also go back and check. So if I actually say, here's a formula, I don't just stick with it. I come back and make sure that it actually still works with this thing right here. All right, let's continue on to add a new kind of summation that really is important. It involves this sigma notation that some of you may have seen. I know this shows up in calculus 1 and 2, and it shows up in college algebra. It's pre-calculus. It's in there. So it means we're going to add things up. Namely, we're going to start at when the index, so this is going to be a variable of my summation, k, is just a variable. And I'm going to start with k is m up to k is n. So k, again, is going to be the index of my summation, and there's a lower value it starts at and an upper integer it starts at. Counts by integers. So to see how this works, let's look at a specific example. So let's look at this first example right here. So let's look at A, and then I'll let you do B and C on your own. So if I did A, that note that it starts at 1 and it goes up to 5. So that summation is actually going to equal A sub 1 plus A sub 2 plus A sub 3 plus A sub 4 plus A sub 5. And now I just substitute them back in with the information that's given at the top of the page, which is negative 2 plus negative 1 plus 0 plus 1 plus 2. Doing some fast and horrible arithmetic, it's 0. Boom! That was easy. So I simply substituted in. So I want you to try to do that now for B and C. Go ahead and pause the video. Can you find those two summations? Notice here, quick note, what is the index of A? Try it. Go ahead. All right, so hopefully you did that. And let's talk about what they are. So the second one, it starts at 2 and goes to 2, which is only the A2 term. The A sub 2, which is negative 1. That was easy. I didn't have to really add anything. So if these two, the lower limit and the upper limit, are the same, it's really just one single value. If they're different, then obviously you're going to have to add something. This one goes from 1 to 2, and that tells me I have two different values I'm going to add together, when k is 1 and when k is 2. If I plug in k as 1, it's actually a sub 2 times 1, which is a sub 2. And when k is 2, it's a sub 2 times 2, boom, which is a sub 4. So it's an a sub 2 plus a sub 4, which is 0. So we have multiple things we can play around with this and kind of manipulate. Let's talk about two more differences. So here is a very explicit formula, because notice in both these things, I'm starting somewhere, 1 and 0, and I'm ending at 5 and 8 respectively. And I just plug them in, do values. So let's look at the first one again to really illustrate what this looks like. If I want to compute this, I literally just plug in 1 for k, so I get 1 squared, plug in 2 for k, 2 squared, keep plugging in for k, 3 squared, 4 squared, 5, we hit our top number, 5 squared, and now I have to square all these, add them together, and I get 55 as my magic value. So it's a bunch of arithmetic, but really it's just a bunch of little steps that we add on. Real quickly, we'll talk a little more about this later on in this chapter, but something called recursion, because each one is actually adding on the next term to the previous steps you've already done for the summation. It's kind of nice. Now, what do we do though if the upper limit is a variable? Well, we use that ellipses again. So let's look at what that means. So let's say I have this n. What does that mean? What's that mean? So remember, I'm doing this as a general formula. It means it starts at 0 and it goes to whatever n value I want. So it would literally, I would write it out like this. When it's 0, it's going to look like this first term. When it's 1, it's second term, third term, fourth term. Sorry, 0 term, first term, second term, third term, dot, 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 which means that pattern continues until we plug in n. Now it can do the actual calculations for each of these little things, and we get this situation. And then we continue simplifying, we get this, and we notice that it's really 1 minus 1/2 plus a third minus a fourth plus a fifth. You get the idea. We keep going on forever with this wonderful formula, and now we can play with it. All right, I have a challenge for you. I want you to take this, and can you write this as a summation? Hint, you're going to need to decide where you want to start the summation and where you want to end it at. Go ahead and pause the video. Try doing this as a summation. All right. So let's say you're trying to do the summation. You should have gotten something that looks kind of like this, where you'll notice if I say it as the first starts at, because this is n plus 0, and this is n plus 1, n plus 2, and so forth. This is really n plus n. So if I look at it from that standpoint, it's n plus whatever I'm adding on. And I'm starting adding 0 and I'm adding n. So my index is I equals 1 to n. By the way, we do not use index x ever. Common indexes are I, j, k, n, and m. I'm just telling you right now, those are the common ones. Again, you have to be careful. I could not use an index of n because I already have n as a variable within my situation. So just like we mentioned in proofs, we cannot double use a variable with two different names. We have to be explicitly clear. Index and variable cannot be the same. All right. So we have these situations, and this actually would be the closed formula for our particular situation. So let's talk about this for a second. In this situation, our top variable is free. It's actually allowed to change. We just need to be anything bigger or equal to the bottom index or lower limit. And that allows us to act on these things a lot more. On the contracts, the index variable of these examples is bound by the summation symbol. Meaning when I give you the summation symbol, I now identify what that index variable is. And it takes every value going from the bottom to the top. Whereas the top index n is a free variable. Remember, it could have been any value, but here, n could have been any number bigger than 0 or equal to 0. So it could be 0, 1, 2, 3, 4, 1,539. You pick an integer. But as soon as I decided it became the index in here and it was fixed. So this is a free variable. This is our index variable. Okay. So those are a couple things to kind of understand and how they're kind of play major roles in this. So I just want you to stop for a second and look at this final example, this example right here. What is the value of 2 to the 0 plus 2 to the 1 plus 2 to the 2 all the way up 2 to the n? Well, could you write this as a summation first off? Well, hopefully you could. If I wanted to write this as a summation, I could literally write it as a sum starting from I equals 0 up to n of 2 to 2 sub I. Okay, so we now have the summation notation. When n is 0, obviously it's just 0 to the 0, which is 2 to the 0, which is 1. Okay. And now notice if we do it, if it's 1, it's 2 to the 0 plus 2 to the 1, which is 1 plus 2. The next one would be 1 plus 2 plus 4. And we can continue on and we can say, okay, what is this more? What's the pattern we're starting here? Is 1 plus 2 is 3. So this is 1, 3, 7, and so forth. And it turns out there's actually some really cool pattern here. So we play with these things over and over and over again because we're trying to get more comfortable with them. Now, what if I do something like this? And this is where I want, because we're going to utilize this later on. This first term is actually kind of a trick. It's a trick because this is my summation. And then I'm adding to that another term. Well, notice what I'm really doing. This first summation, this thing right here is going to come to be 2 to the 0 plus 2 to the 1 plus 2 to the n. That is going to be that part. And if I add on to that 2 to the n plus 1, that's the same thing as if I had just added up the whole time from 2. Oh, I don't mean that. From k equals 0 to n plus 1 of 2 to the k. Can you see how this right here just turned out to be this chunk right here, and then I added on that extra term and turned it back into this? Similar to this one, I could start this as this is going to be 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus, I'm going to do two terms here on the end. I'm going to do 1 over n squared and 1 over n plus 1 squared. So it says separating off the final term. So that's this term right here. So how could I write this chunk in parentheses as a summation? Go ahead and pause the video and write that as a summation. Go ahead. All right. So if you did that, you would have ended up with this summation. And the key thing is this ability to break off a term and put it back on becomes highly valuable for an idea that we're going to do in our next section called induction. It's going to play a lot of roles in that. So each of these sums of terms of difference of two quantities, some sums are actually subtractions. And when we expand them out, sometimes they cancel out everything except the middle and the end. These are actually called telescoping. So this right here, if I have the term 1 minus k minus 1 over k plus 1, you'll notice it's equal to 1 over k times k plus 1. Okay, so the reason this is important is because if I asked you to find the summation, remember equal signs go both directions. So I can literally start with this portion of the identity. I can replace this with this and then replace it with this. So it would look like this. So I can take this part and replace that 1 over k minus 1 over k plus 1. Well, as you plug in every k, notice I'm going to have 1 over 1 minus 1/2 when I plug in 1. Okay, that's when k is 1. This is when k is 2, k is 3, k is 4, k is k is n minus 1, and k is n. Notice what this is: minus 1/2 plus 1/2. Those go away. Minus 1/3 plus 1/3. Those go away. This would keep canceling all the way up until I have minus 1 over n plus 1 over n. So it turns out this whole summation here is just the first and last. And that is a useful kind of concept. All right, I know this video is getting a little bit longer, but I want to hit one more key thing when we talk about sequences. We talk about summations. Let's add products. So when we did summations, remember we used S, sigma, the Greek symbol sigma, which did start with an S. So for products, product starts with P. So we use pi. So if I do this, it's just the same idea as summations, except instead of adding them, I multiply them. And so this idea of being able to multiply over and over and over again is really, really cool, where I can break off a term, we can multiply them back on. So if I have this where I'm multiplying the first 5 numbers, this is really going to be 1 times 2 times 3 times 4 times 5. And then this one is going to be just one term. So it's one, remember it starts and ends of the same thing. So it's actually just the 1/2 term, whereas this is multiplying all these together. The reason this is important is because of some key concepts that we can actually use. namely the factorial. So the factorial and the n choose r are going to be some things we're going to use. I'm just going to introduce them here and how to compute them. A little more about them we'll give when we get into combinatorics and counting. But the factorial notation, if you've ever not seen it before, is this n exclamation mark. And it literally means to multiply all the values from n all the way down to 1. The one thing that throws it off is this 0 factorial. 0 factorial is 1. Why? Again, the n factorial is actually based on counting something very specific. And I cannot show you that until I get to that concept a little bit later on. But you will notice if I simply list out the first several factorials, 0 factorial is 1, 1 factorial is 1. But notice 1 factorial is 1 times 1. 2 factorial is 2 times 1 factorial. 3 factorial is 3 times 2 factorial. 4 factorial is just the 4 times the 3 factorial. But notice how fast these grow. These are one among the fastest growing things. They grow faster than any exponential function, and they are super powerful. And thus, they are really occurrent in a lot of discrete mathematics. They are also a recursive function, and we can define it this way. N factorial is 1 if n is 0. Otherwise, it's n times the previous factorial. And this is really useful if I go to something like this. So let's talk about this first thing right here. 8 factorial, a way to think about 8 factorial, remember, is that 8 factorial is really 8 times 7 factorial. That's what the 8 factorial is this equivalent to. If I put that over 7 factorial, well, the 7 factorials are going to cancel out, and that's just 8. What about this thing right here? Well, this would be 5 times 4 times 3 factorial, because I can break off the first two terms, put that over 2 factorial times 3 factorial, and now suddenly these things cancel out, and now I'm just left to compute what's left, and that would be 20 over 2, which, by the way, happens to equal 10. And we can calculate that out. It's really easy to figure out. So factorials are really, really useful. I can even use those properties here because this is the same exact idea as this one. It's just as more generalization. Similarly, this one is also similar. I can just break off more things and keep working on them. All right, so the way we can attack these things is just little by little, again, by using these formulas to our advantage, we can get them in the same common spot. All right, so let's talk about one last thing, and that's called n choose r. Again, I'm not going to get into this a lot more. This just comes up a lot more in combinatorics and probability. But n choose r means I have n things, I'm choosing r of them. I have n total elements, and I'm choosing subsets of size r. How many subsets are there? This is what this counts. Computationally, that's going to be n factorial over r factorial times r minus n minus r factorial. We're going to compute these values in this chapter. What they are, we'll get to that a lot more. Again, so you're going to treat them right now just as a number, computing. Do not worry about that. So again, let me do a quick example because I don't want this video to drag on too long. This first one would literally be 8 factorial. So you put the first number on top over 5 factorial times 8 minus 5 factorial. So that is going to be 8 factorial over 5 factorial times 3 factorial, because that's what 5 minus 3 is. But again, what we already know is that 8 factorial is 8 times 7 times 6 times 5 factorial, all that over 5 factorial times 3 factorial. Well, the 5 factorials cancel out. It also turns out that 3 factorial is 6, so those will cancel out, and that's just going to give me 56. So 8 choose 5 turned out to be 56. On the other hand, 4 choose 4 is where you have to remember that 0 factorial is equal to 1. That does come back up. We will be using this. Again, if I ask you to compute these things, I'm not giving you crazy big. I want you to just understand the basic concepts, okay? All right, one last thing I do want to make a comment about coming back to this. This is the most common notation. However, there is one other notation you do need to know about because your book does sometimes use it. I don't really agree with it, and nor do most discrete, but yours does because it's actually more of a probability thing in statistics, where they do NCR. They're trying to do this choose function. It's trying to be this idea, and it doesn't. But what is C? Like that's a really horrible. I've also seen this written as C of and R. Again, what is seed? You have to define that very clearly. That's not clearly defined. So it kind of breaks the idea, and I'm not going to use it very much. I'll tell you on the tests and so forth. I want you to use this notation. You can change it into this right here, but ignore these things. If you go looking on videos, you're probably going to find them. They're there. All right. That's the end of that. Please let me know what questions you got. Good luck.